Welcome to AI Paper Slop, the series where we summarize the absolute bleeding-edge AI and tech papers for you. If you're a technical person, an ML engineer, a researcher, and you need to stay sharp but don't have time to read every preprint, you're in the right place.
We are jumping straight in today.
Straight in. The paper for this deep dive is called Understanding and Mitigating the Video Action Generalization Gap via Temporal Ratio by researchers over at Georgia Tech and Amazon FAR.
And let's just give you the core insights right up front. The fundamental problem this paper tackles is with generative video foundation models, or VFMs.
Right.
These models have incredible compositional priors. They understand the world. But when you fine-tune them into video action models, VAMs, using actual robotic data, they just lose those priors.
They just forget it all.
Exactly. It creates this massive video action generalization gap, or VAG gap. And the researchers figured out why. The action head is essentially just ignoring the predicted video futures.
Which is wild. So their diagnostic for this is what they call the temporal ratio, or TR. It's this attention-based metric that actually calculates how much the action head relies on those future latent frames compared to just the clean current frame.
Yeah, and the TR naturally fluctuates based on what phase of a task the robot is in. It's high during planning, and it's super low during precise manipulation.
So the solution they came up with is TR adaptive guidance. They dynamically amplify the compositional video conditioning using flow matching guidance, but, and this is key, only when that temporal ratio is high.
And that single trick mitigates the out-of-distribution gap on the LIBERO benchmark and even real-world bimanual tasks.
It's honestly a brilliant fix. But to really grasp how they did this, we have to step back. We need to look at the specific architecture they're probing, because to fix the gap, you have to understand how it fails.
Let's break down the setup. They are using a 28-block Cosmos Predict 2.5 2B diffusion transformer as the video backbone.
The world simulator, basically.
Right. It generates these partially denoised latents, and then it feeds those into a 300 million parameter Gemma transformer action head. And that's trained via flow matching.
But the issue is that existing policies just aggressively overfit to visual correlations, right? Like object coordinates.
Oh, completely. The backbone knows physics, it knows how objects relate, but the action head just overwrites all that generalized understanding with rigid, memorized spatial behaviors from the training data.
The concrete example they gave in the paper really made this click for me.
Yeah.
Say you train a policy on the primitive task, put the cream cheese in the bowl.
Okay, yeah.
And then another task, like put the bowl on top of the cabinet. The model has seen the cream cheese, the bowl, the cabinet. It knows how to grab them.
It has the primitives.
Right. But if you give it the novel instruction, put the cream cheese on top of the cabinet, it just fails. It has all the puzzle pieces, but it literally can't snap them together.
It's basically the LLM equivalent of memorizing code snippets. You ask it to output function A, flawless. Function B, flawless.
But combine them into a slightly new script, and it just throws a syntax error.
Exactly. The generative prior is just gone. And if you're listening to this and building foundational robot policies, the major takeaway here is that you can't just scale your way out of this.
Right. Throwing more compute at it won't fix it.
No, because if the model fundamentally loses its generative world knowledge during the action fine-tuning phase, more data is just, it's just reinforcing the memorization.
So knowing that this gap exists, the researchers decided to systematically test the design space. They tried brute forcing a solution by tweaking all the training and inference parameters.
And the results from their ablation sweep were incredibly messy at first. The performance landscape is just fragmented.
Let's dig into that ablation. Yeah. They looked at fine-tuning strategies first, right? Full fine-tuning versus Lurai.
Yeah, and you'd think full fine-tuning on the target actions would work best.
That's what I would assume, yeah. Get the model aligned with the exact hardware.
But it actually destroys the pre-trained temporal structure. It aggressively overfits to the in-distribution data. What actually worked best was joint aura.
Joint Royale.
Yeah, training just like 2 to 6% of the parameters at rank 32. That yielded the absolute strongest out-of-distribution performance.
Because it preserves the backbone's world model while still letting the action head map to the physical joints.
Exactly.
Okay, but the inference sweep, that's where I found the most surprising result. They swept the video noise level, the sigma V, and found this extremely specific Goldilocks zone.
Yeah, the performance peaks sharply at an intermediate video noise level of 0.883.
Which is such a specific number, 0.883. What happens if you push the noise higher like closer to 1.0.
Well, at 1.0, it's pure Gaussian noise. So if the noise is too high, the future latent tokens just lack any temporal structure. It's static.
So the action head can't use it anyway.
Right. It's forced to ignore the future and anchor its decisions purely on the high-resolution present state.
But wait, if you go the other way and drop the noise down toward 0.0, shouldn't a perfectly clean image give the action head better data?
You'd think so. But it makes the policy incredibly vulnerable to confident hallucinations.
Oh, because if the world model gets the future slightly wrong?
Yes. If it demands a clean future and the model hallucinates the handle of a mug is, say, 2 inches to the left, the action head will just confidently follow that hallucination straight off a cliff.
Wow. So 0.883 gives it just enough semantic structure to plan, but keeps enough noise so the action head doesn't blindly trust every pixel.
Exactly. But even with that perfectly tuned noise level, they found this crazy phenomenon, the video action disagreement.
Oh, I loved this part. It's where the video backbone predicts an absolutely perfect, flawless future trajectory. The latents are beautiful, but the action head just straight up ignores it.
It executes a memorized action anyway. It's like having a brilliant AI GPS navigator in your car routing around traffic perfectly.
But the human driver just ignores the screen and turns left into a traffic jam out of pure muscle memory.
That's exactly it. The failure wasn't the world model. The failure was the routing of attention.
Which brings us to the aha moment of the paper. A correct imagined future is totally useless unless we can mathematically quantify if the action policy is actually looking at it.
We need to know where the driver's eyes are looking.
Right, and that leads directly into their core contribution, the temporal ratio. Let's unpack the math behind this TR metric.
So it's a direct measure of attention mass. In the Gemma action head, they partition the video tokens into 2 sets.
Set 1 is V0, right? The anchored current frame.
Right. V0 is the present. Set 2 is V+, which contains all the tokens for the predicted future latent frames.
And the temporal ratio is just the softmax attention mass assigned to the future, divided by the attention on the present.
Exactly. It's a ratio of how much the model is daydreaming about the future versus staring at what's right in front of it.
And I noticed they specifically pulled this ratio at layer 15 of the Gemma action head. Why layer 15?
The ablations across the layers are really revealing. The early layers, like layer 1 or 5, they just distribute attention evenly. They're just gathering context, totally insensitive to the noise level.
Just general feature extractors.
Yeah, but by layer 15, the network has to make hard routing decisions to actually output a physical action. At that layer, you can actively watch the attention mass shift between the current frame and the future.
And the physical mechanics of why this works natively is because of the denoising setup itself. The current frame, time t equals 0, is injected as a clean, high-signal anchor.
It has zero noise. It's reality.
Right. But the future frames, t greater than 0, those are noisy. They're the model's imagination.
So TR physically measures the model's instantaneous choice. Do I trust reality, or do I trust my noisy statistical imagination?
And the fascinating property of this ratio is that it organically separates the phases of a task. It spikes during the planning phase.
Yeah, if the robot is reaching across a cluttered table, it needs future context. It needs to know spatial relationships over the next 3 seconds, so TR goes up.
But then, right when the gripper is about to close on an object,
the TR just plummets.
Because at that exact moment of precise manipulation, you want the model anchoring to the present high-res frame.
Yeah.
You don't want it grasping based on a noisy imagination.
Exactly. And for you ML engineers listening, this is a masterclass in using implicit attention metrics.
Totally. Instead of just looking at post-hoc success rates when an episode fails, you have a live, real-time diagnostic signal during inference.
You can read it at 10 hertz and know instantly if the policy is planning or reacting.
Which is huge, because once you have that real-time signal, you can dynamically intervene. Which brings us to their solution, TR adaptive guidance.
Right, so we know when the robot is ignoring the plan. To force it to follow the compositional video priors, they apply velocity space, classifier-free guidance, or CFG, inside the action Euler loop.
And they use 2 types of guidance simultaneously. First is language guidance.
Yeah, it's like a steering assist. It extracts the exact pull of the specific language command.
And the second is plan guidance. This part is cool. They query the video model with a heavily extended horizon, pushing it out to t prime equals 24 latent frames.
That's about 2.4 seconds of deep imagined future And then they truncate that back down to the policy horizon of t equals 5, using that dense structure to guide the action velocity.
But here's the clever trick, and I think this is where a lot of people would mess up. They don't apply flat guidance.
No, flat guidance is catastrophic for in-distribution performance.
Right, because if you force the model to constantly follow the plan with a high guidance weight, you're forcing it to hallucinate during the grasping phase.
It's like forcing the driver to stare at the GPS while they're parallel parking. They're going to hit something.
Exactly. So they scale those guidance weights dynamically based on the live TR reading. At the start of an episode, they calculate a baseline TR, kind of like a resting heart rate.
And if the live TR drops below that baseline, meaning the robot is in a reactive grasping phase, the guidance scaling factor instantly drops to 0.
The steering assist turns off.
The model just acts purely on the current frame.
But if the TR rises above the baseline, the robot is planning weight, the guidance is amplified. It mathematically forces the model to follow the compositional video plan.
And they cap that amplification at a max of 2.0, so the trajectory doesn't become too rigid.
It's incredibly elegant. You turn the screen off when parking and turn it on when navigating. But does it actually work in the real world?
The results are super compelling. In simulation on the LIBERO benchmark, it boosts average out-of-distribution performance by about 6%. And it doesn't degrade the in-distribution success at all.
But simulation is one thing. They put this on a real bimanual VAMs setup. We're talking 12 degrees of freedom, 2 arms, running at 30 hertz in messy, real-world physics.
Yeah, they deployed their optimal config, the joint LIBERO, the sigma v at 0.883 and t equals 5. And across real-world compositional tasks, just adding this inference-time guidance bumped the average success rate from 71.7% to 83.3%.
A huge jump just from an inference-time intervention.
And it beat massive scaling law baselines. Models like Pi0 and Cosmos Policy trained on the exact same compute budget of 1 million optimizer steps across 32 H200 GPUs.
Wow. Beaten by clever attention routing.
It really proves that dynamic routing can punch way above its weight class against brute force scaling.
So just to synthesize this whole journey for you before we wrap up, we went from a fragmented performance gap where VAMs forget their priors to a mechanistic understanding of video action disagreement.
The GPS problem.
Right. And then to temporal ratio as a live diagnostic, and finally to a dynamic inference time solution that actually works on hardware.
It really highlights a systemic vulnerability in how we map world models to physical actions. And it actually brings up a final, somewhat provocative thought, which I pulled directly from the author's limitations section.
Oh, I love the limitations sections. What's the catch?
Well, we're relying on TR adaptive guidance to amplify the predicted future when the model is planning, right?
Right.
But think about how video foundation models are evolving. As they get more advanced, what happens when they hit a severe distribution shift? They don't just fail quietly. They start generating physically impossible futures with massive, unwavering confidence.
Ah, right. The classic hallucination problem, but scaled up to physical space.
Exactly. Under this specific TR adaptive framework, if the video model confidently hallucinates a future where the robot arm phases directly through a solid wooden table, the TR signal would still spike.
Wait, because the model is technically still planning a trajectory.
Yes, it's looking forward. The system would see that high TR, it would aggressively amplify that hallucination via flow matching guidance, and it would drive the real-world robot to attempt a physically impossible, highly destructive action.
Oh, wow. Because the dynamic guidance mechanism is mathematically blind to whether the future is actually physically plausible. It just knows the model is looking at the future, so it hits the gas.
Exactly. It raises this massive open challenge for anyone building in this space. How will the next generation of world action models filter out confident but impossible futures before the action head blindly follows them into a disaster?
If the AI GPS is confidently telling you to drive into a lake, how do you teach the car's steering column to verify the map? That is a phenomenal question to leave you with. Thank you all for tuning into this deep dive on AI paper slop. If you want to see the exact layer-by-layer attention maps or the math behind the flow matching, definitely go pull the original paper. We will see you next time.